For example number 3, we have a moving particle and starts at an initial position defined by the vector r of 0 equals 1, 0, 0, and with an initial velocity r. Actually this one should be a v, but I think your paper might be updated, not mine. Whoops. So this should be v of 0, right? I think yours is updated, right?
Yeah.
Okay, perfect. 1, negative 1, 1. And its acceleration, there's a couple of typos here. So its acceleration, a moving particle. And it's given by this vector valued function, a of t. Well, like I mentioned before, in this case, we're going to go backwards. So we're going to go from acceleration, integrate this, get the velocity, do the initial value problem with 3 components, integrate it a second time, and get the position function. So, and in this case, at just a value t. It doesn't matter what value. So, number 1, let's get the velocity. So for the velocity function, v of t, this will be nothing other than the integral of the acceleration, alright, which will be the integral of 4t plus 1, 6 root of t, which, you know what, I'm going to change this to t to the 1/2 and negative sign t with respect to. Alright, so let's integrate component by component. Well, we're going to have the following. This is 2t squared plus t plus, let's call this a c1 because we're going to use different, I'm going to have enough space here, different constants of integration. That's 2t squared plus t plus c1, comma, the integral of t to the 1/2, isn't that t to the 3/2? And 6 over 3/2. But 6 divided by 3/2 is the same as saying 6 times 2/3. That is 6 times 2, which is 12, divided by 3. So that's going to give us a 4. And that's with the corresponding c2. Then from here, the integral of sine, be careful because the integral of sine is negative cosine, but times that negative in front of the sine, that should be positive cosine t, and then plus c3. Okay? Now, so we're going to use the initial condition because, well, this is the velocity function, v of t, and we are going to use the condition that v of 0 equals to 1, negative 1, 1. That is, with v of 0 equals 1, negative 1, 1. That is, when t equals 0, x equals 1, when t equals 0, y equals negative 1, when t equals to 0, z equals to positive 1. So we're going to substitute for each component. Well, so this will be 2t squared, that is 2 0 squared, 2 times 0 squared plus 0 plus c1, that should be equal to 1 in this case. This means, well, everything else is 0, c1 equals to 0. Okay.
Before the 1, negative 1, 1, what is all of that? Are those V's?
This one?
Well, the one before it, like there's a little sentence. It just looks weird from where I'm sitting, I think.
With? Oh.
With. Oh, okay.
With, oh, yeah. Yeah, might be the perspective. You know, it's actually weird. It's right. With, yeah, with v, yes, that's initial condition. Okay, so let's do the second component. 4 times 0 to the 3/2 plus c2 equals to, in this case, the y component of the vector, which is negative 1, careful, All right, let's do this component by component where it corresponds. And well, this is going to zero out C2 equals to -1. All right. And last but not least, for cosine 0 plus C3 equals to, in this case, 1. But what's cosine of 0? Isn't that 1? Plus C3 equals to 1. That means C3 equals to 0. All right, so we're going to use these constants of integration. Let me highlight them so you can relate each of them. C1 equals 0. It's going to be the C1. And C2, -1, will be the C2. And finally, C3 equals to 0 will be this C3. Yes, it's 1. Yeah, I don't know what happened with that one, but yes, so that's C1. So let's go back to the velocity function, v of t. And write it with the corresponding constants C1, C2, and C3. So that's 2t squared plus t plus C1, which is 1, comma, 4 times t to the 3 halves plus C2, which is -1, and cosine t plus 0, which is C3, which is just cosine of 3. No need to write the 0. Okay, so we got the velocity function. That's one part of the problem, one part of the answers. The next one is to recover the position function. And well, from the same idea, we know that position, okay, that was number 1. Number 2, it's position, it's r of t, equal to the integral of the velocity with respect to t. That is, the integral of this vector valued function that we just found in the previous part. So that's the integral of 2t squared plus t plus 1, comma, 4t to the 3 halves minus 1 cosine t with respect to t. All right. Well, integrating each term, the integral of 2t cubed, that's going to be 2/3 t cubed plus t squared over 2 plus t, and well, plus a constant of integration, but we already used the letter c. So you don't get confused with the same constant. How about we just use another letter? Let's use, I don't know, k1. All right, just so we don't get confused. Then, so that's 4 times t to the 3 halves. Oh, wait a minute. The integral of t to the 3 halves, t to the 3 halves plus 1, is that 5 halves? Over 5 halves. But well, let me simplify in the same step. So dividing by 5 halves is the same as multiplying by 2/5. So that's 4 times 2, that's 8/5. So 8/5, and minus t plus k2, and the integral of cosine, which is sine t plus k3. And we're going to use the same, we're going to do the same as we did with but in this case we're not going to use the velocity vector because we want to retrieve the position function. We're going to use the condition for the position, which is the other vector that is given. That's r of 0 equals 1, 0, 0. Right? Yes.
For the 2 plus 0 plus 3, 1, does that say 1 or -1?
Which one?
The one on the left, the purple one?
This one? It's a v of 0.
Yeah, for the 2 0 squared plus 0 plus 3, 1 equals 1. Is that k1 or -1?
And
The purple one?
the purple one, oh, it's 1. It's 1. Yes, because we're equating it to the x component of the given vector, which is +1. The one that we equate to -1 is the y component, because in this case that's the -1.
Okay, thank you.
My pleasure. So let's okay, so let's use r of 0. That's 1 0 0. Okay, so number 1. Okay, so 2/3 of 0 cubed plus 0 squared over 2 plus 0 plus k1 equals 1. That means k1 equals to 1. On the other hand, 8/5 of t to the, or not t, actually it's 0 to the 5/2 minus 0 plus k2 equals to the y component of the vector, which is 0, which in this case is going to be k2 equals to 0. And last but not least, for the z component, that sign of 0 plus k3 equals the z component of the vector, and well, that's 0. And sign of 0, which is 0, that means k3 equals to 0. And again, let me highlight every constant just so you can see which one is which. K1 is going to be this K1 right here. K2, it's going to be this K2 here. And K3, it's going to be this K3. Alright, so we're ready to go back to just put the constants where it corresponds. Are the position function, which is 2/3 t cubed plus t squared over 2 plus t plus 1, and 8/5 t to the 5/2 minus t plus k2, which is 0. That's just, we don't write anything, and sine t plus k3, which is 0, but we don't need to write the 0. And so yes, we were not going to make it through this problem on time last night, right? I mean the other night. So it's kind of a long one. It's basically a Calc 1 problem where you were finding the constant of integration, but in this case, well, we're doing it 3 times, right? Or 6 times, if you will. So what's next over here? So there's a couple of types of parametric forms that we're going to be using more often than not. One very, very typical that we use, and we have used it already quite a bit, is the linear motion, right? And well, we already described the equation of a line in 3 dimensions, and well, we got that we need an initial point and a vector in the direction of the line segment. And well, the components of the vector are the values that multiply t, which is like the slope. But recall that we don't have slope in 3D, at least for the linear. It's rather a direction vector, and the initial point. Well, from here we can take the derivative of that linear equation. So the derivative of these constants is 0. And the derivative of a times t is just a, the derivative of b times t is just b, so that's just going to be the direction vector. And the acceleration vector is, well, the derivative of the velocity, which is just the 0 vector, right? And then we also have, let's see, we're going to have the circular motion, which is another one that we're going to use a lot. So that's going to show up more often than not. So number 1, you might want to consider the parametric equation of the circle, which we actually discussed quite a bit at the end of the semester in Calc 2, when we described parametric equations. And well, this comes from the fact that the circle in this orientation, in the counterclockwise direction, well, for the unit circle we have cosine theta, sine theta. That is all the points that lie on on the unit circle at any angle, well, are of the form cosine sine, where the x value is the x value of the point is this cosine function, the y value is the sine function. But of course, not all circles are unit circles. We can describe this as a circle of radius r. So let's call it big R. And of course, this is also the vector form. This was in this same order we described the parametric equation version of the circle, and also in this direction. Let me point the direction. And counterclockwise direction. So what are we going to have? Okay, the velocity, well, take the derivative of each component. Well, the derivative of cosine, it's a negative sine, and the derivative of sine, it's cosine, and the acceleration vector is going to be of the form negative cosine, negative sine, well, with its corresponding multiple for the radius of the circle. Well, but there's a couple of questions that we might want to further discuss for a few points here. So what's the relationship between the position and the velocity vector? Well, number one, and we're gonna go with the signs in this case, the signs of the vectors. Well, number one, the position vector, so we're gonna go from the origin to whatever terminal point on this, which is going to lie on the circle. All right. Well, from here, from this point, okay, let's call this R. All right, the vector R. So that's the position vector. All right. What's next? The velocity vector. So from this point, we are going to go negative units in the x direction and positive units in the y direction. So let me use a different color for this. All right, so that's going to be this vector. Okay, that's the velocity vector. And number one, from this same point right here, the acceleration vector is going to be a vector in the direction of negative x and negative y. That is, from here, negative x, negative y. This is basically going to be, it's actually going to overlap with the position vector, but in the opposite direction. So from here, let's see, the position vector and the velocity vectors. What can you notice about those two vectors? They're perpendicular, right? They're orthogonal because they form a 90 degree angle. They're orthogonal. And what about the position and the acceleration vector?
So the purple one is the acceleration.
Yeah, let me label it. Yes, that's acceleration. That's letter A. So what about? Let's see. Okay. So can you repeat that, please?
They have the same magnitude?
They have the same magnitude.
Opposite direction?
Opposite direction. Well, they're, yes, in the just opposite direction. Another way to say this, these are parallel. Alright.
So they don't overlap, they're parallel then.
Yes, exactly. Yeah, well, they basically overlapping, but I just didn't make them overlap here so we can distinguish between the two of them. Okay. Well, so also, what's the dot product between the position vector and the velocity vector? 0, right? That's the condition of orthogonality, right? So different ideas that we are going to discuss about circle. And of course, these same ideas are going to be extended to the 3D version of the circle, which is the sphere. Alright, so let's look at one example of this. So we have an object moving on the trajectory described by this vector valued function. Alright, so let's show that the object moves on a sphere and find the radius of the sphere. So that is, we're going to find the magnitude of this vector. That is the square root of the x component squared plus the y component squared plus the z component squared. And well, this will be the square root of 16 sine squared t plus 25 cosine squared t plus 9 sine squared t. So, in this case, combining like terms, we can combine 16 sine squared plus 9 sine squared. Isn't that 25 sines? 25 sine squared t plus 25 cosine squared t. And that's what we can factor out a 25 and sine squared plus cosine squared. What's that? 1, right? So this is equal to 1. 1 times 25 is 25. And what's the square root of 25? 5. So that means we're getting a magnitude of 5 from the initial point, in this case the center of this of the object. Well, in this case it's a sphere because we have 3 dimensions. So that's 5. So from any point there's 5 units. That means we have a sphere in this case. All right. So let's find the velocity and the speed. Okay. To find the velocity, we need to find the derivative of the function, that's our r prime. And well, the derivative of 4 cosine, that's 4 sine. And negative 5 sine. Oh, wait a minute, it's 4 cosine. No, I was thinking of the second component already. Negative 5 sine and 3 cosine. Okay, so that's the velocity function, and they also want us to find the speed. And then recall that the speed is not a vector. The speed is actually a magnitude. It's a scalar, so that's the magnitude of the vector, of this velocity vector. So that's the square root of, well, I'm going to just simplify this. So that's 16 cosine squared plus 25 sine squared t plus 9 cosine squared. And well, that's we have another same identity here. So that's 25 sine squared t plus cosine, 25 cosine. And well, this is the same result as before. That's equal to 5. So the object moves at a velocity with a speed of 5, well, units of distance per unit of time, right? Just to put some context, some units in the context. All right. Okay, so for the last page for this, the last couple of pages we're not done yet. I thought we were okay. So projectile motion, a very classical problem here in, well, pretty much in intermediate algebra. That's something that you deal with. You're given the second degree equation or function, and they give you values to plug in for an initial velocity, an initial position. You get to see these equations again in calculus when finding max and mins, maximum speed, maximum velocity, etc. And well, you also get to derive these equations in your physics class if you have taken that class. Well, and what's number 1? In this case, we're going to consider the 2-dimensional case, projectile motion. And in this case, well, we are going to neglect many other aspects like temperature or crosswinds, So we're just going to consider the gravity, the force of gravity, which is, well, there's actually 2 values, 9.8 meters per second if we're using the decimal system, the metric system, or 32 feet per second, meters per second squared and feet per second squared. All right. Well, so to derive this equation, let's assume that the object has some initial velocity, that is v, the velocity at 0, that's initial velocity, some u sub 0, v sub 0, whatever those components are. Those are going to be some numbers that will be given some identity later. Well, and it has an initial position r, which is position, and x initial, y initial. So we're going to work only with symbols. So basically what are we going to do? So we're going to solve this initial condition problem twice, but this time we're going to do in the context of projectile motion. So this is how we're going to start. If we were to, okay, any ideas? If we were to start, well, we're going to start with from acceleration to velocity, and then from velocity to position. What would be the acceleration vector in this case?
0, 9.18, 0.
Mm-hmm. So it would have an x component of 0 and a y component of, well, let's call it negative g, all right? Regardless of whether we use the metric system, the decimal system, the metric system, or the English system, either way, all right? So from here, to find the velocity, let's integrate the acceleration, which is the integral of the vector 0, negative g with respect to t. That is the integral of 0. What's the integral of 0, by the way? Just a constant, right? So just a constant. So let's call it c1 and minus gt plus c2. All right. Well, so it may not be that obvious. That's one question then that once my calculator asked, and I was like, oh, interesting. So the integral of 0 with respect to t. Well, I can take the 0 outside of the integral, and the integral of dt is t, but 0 times t, isn't it? Oh, plus c1 or plus c. So 0 plus c, it's just c. So that's why the integral of 0 is just a constant. It's kind of a weird question, right? I know. All right, so, well, we got the velocity function already. So with v initial, that's the initial velocity given by the vector with components u initial, v initial. Well, we're going to set, in this case, well, so we don't have any t's to plug in here, you know, so c1 equals u0, all right? And on the other hand, negative g times t, which is 0, equals v initial. That means 0 equals, or rather, oh, I forgot the plus c2, equals v initial. 0 plus c2 equals v initial, and c2 is simply v initial. So we may go back to, I might need some space over here. Oops, no. So we may go back and write our velocity function. This means that the velocity function equals c1, which is u initial, comma, negative gt plus v initial. And I think this equation looks familiar from physics, right? From linear motion in this case, and also the other, all those equations rather. Okay, so to get to the position function r, what do we need to do? Integrate the velocity function. And we know the velocity function. That is, we're going to integrate u initial, comma, negative gt plus v initial with respect to t. Well, that integral will be u initial t plus, well, I'm not going to use the same c, I'm going to use k1, comma, gt negative 1/2 gt squared plus v initial t plus k2. All right. And well, to find out the constants k1 and k2, we're going to repeat the process that we did for the initial condition for the velocity, that is initial velocity, but this time we're going to do it with the initial position this time because we want to retrieve the initial position. So with a initial, oh no, not a initial, actually r initial, that's the vector x initial, y initial. Well, on the one hand, so u initial times 0 plus k1 equals to x initial. That means, well, k1 equals to x initial, and on the other hand we have negative 1/2 g times 0 squared plus v initial c times 0 plus k2, that should be equal to y initial. And well, everything here is 0 except k2, and that equals to y initial. So we have already a position function r of t equals to u initial t plus x initial, comma, negative 1/2 g t squared v in plus v initial t plus y initial. And well, especially the second component of the vector, I think this is a formula that we use in physics for projectile motion. That's the same formula we use in intermediate algebra as well to model those situations. But of course, back then we didn't see this in the sense of vectors, and we didn't integrate anything because, well, it was an intermediate course, an intermediate algebra course, and not a calculus course. And even in the calculus 1 course, well, it was just a calculus 1 course, not a vector calculus course. So that's it's, we get back to the same point again with different perspectives. So let's have a look at one example. So let's suppose a baseball is hit across a flat field from an initial position of 2 feet above the ground, and with an initial velocity vector 25,4 feet per second. Number 1, find the velocity and the position vectors. Alright, so number 1, let's see. So let's write this information in terms of vectors. That is, we have an initial position. We have an initial position r of 0, and in this case that initial position is, well, notice it's 22.5 feet above the ground. Will that be the x component or the y component of the vector? The y component, right? Because it's above the ground, so 0, 2.5. And we also have a velocity in vector form, an initial velocity more in particular, that's 25,4. All right. Well, so let's find the velocity function and the initial, and the velocity and the position vector. All right. So in this case, well, we have this vector. In this case, we have the u initial. That's the component of the velocity, and the x component of the velocity and the x component of the position. We can write down r of t equals u initial, that's the velocity, the initial velocity, that's 25. Wait a minute, it's velocity, yes, 25 t plus x initial. The x initial, notice in this case, is 0. All right? That's the x component of the initial position. I'm not going to write that 0, actually, comma, the y equation, which is this big polynomial here, number 1, it's negative 1/2. Oh, what would be the value of g in this case?
32.
32, right? We have two options, 9.8 or 32, but because in this case the problem is in terms of feet, it's given in feet, so we'll use the gravitation constant with feet, that is 32 t squared. V initial, so that's V initial, that's 4, or in terms of y, 4t, and y initial plus 2.5. Alright, so that's our position vector. Well, we can simplify that 32 over negative 2 and make it a negative 16 instead. Alright? And well, to find the velocity function, what would we do to find the velocity function? Take the derivative, right? So that's 25 comma negative 32t and plus 4. Alright? So those are the two vectors here. So we're going to use this information right here to answer the questions, the next question rather. So, number 1, how far does the ball travel horizontally before it hits the ground? Okay, let's draw a picture so we can figure out what we want to find in this case. Well, so the ball is thrown at is hit at a height of 2.5 feet, right? So that means it's not going to be released from the origin, but somewhat high. It's going to do this, right? Okay, and well, so how far? That means we're looking for the x-intercept, don't we? I mean, in terms of the graph, we were looking for the intercept. And well, how do we find the x-intercept of any function? Yes.
We find y at 0.
Exactly. So we set the y equals to 0 to get the x-intercept. We set x equals to 0 to find the y-intercept otherwise. But in this case, we want the x-intercept. So, well, x-intercept, that is, let the y component, y of t, equals to 0. So we're going to go with the y component of the position vector, not the velocity vector, because we want to find the position where it falls, all right? So that is negative 16t squared plus 4t plus 2.5 equals to 0. Well, what do we have here? This is a quadratic equation, and there's many methods to solve quadratic equations, the quadratic formula, or use the graphing calculator. So, I mean, this is not an intermediate algebra class. I really don't want to go through the details. You know how to solve quadratic equations, and in this case, t is approximately 0.5396 seconds. All right? Yes, of course, when we solve a quadratic equations, we are going to get to solutions. In this case, well, we're going to get one positive value. The other solution is going to be negative, but recall that we neglect negative values of times because, well, that's like going back in time, right? So, which doesn't make sense in our context, right? Unless you're friends with Marty McFly, well, travel in time, or Doctor Who, where to the time where the ball was also hit in a negative time, right? But well, that's not the case. Okay? Well, but that's actually the time where it hits the ground. We want to know the position, how far is it? So where would we plug in this value of t? In the x component. In the x component. So, substitute in x component. In x component of what? Of the position. All right, that's going to be simply x evaluated at 0.5396. That's simply 25 times this number, 0.5396, which is approximately 13.489 feet. Makes sense, right? I mean, you hit a baseball, 13 feet. It's not bad. All right. Well, so there's an alternative to this quadratic model, to this motion or projectile motion model. In this case, well, in the case in which we know the initial velocity or the initial speed, and the angle in this case, not the other information like we did before. And well, rearranging the equation, we would obtain this equation. And well, so I think it should make sense on how we would get the equation, because well, this is like r cosine theta, one should be sine, I think. This one is supposed to be sine theta. All right, not cosine. And well, it's like when we convert from polar coordinates to Cartesian coordinates, well, x is r cosine theta and y is r sine theta. Well, in this case, applied to the velocity context, or comparing it with the values from the unit circle. X is the cosine, y is the sine. So, well, this is a formula that, again, you don't have to memorize. So when you get tested on this topic, just write it down in your formula sheet. That's fine. So let's see. Let's have a look at one example. So a baseball is hit from a height. Okay, that's the same problem, but in this case, instead of giving us an initial position and an initial velocity in the form of a vector, they're still giving us the velocity as a magnitude in this case, and the angle, and an angle of 22 degrees above the horizontal. Well, so write the vector valued function representing the path of the baseball. Well, so all we have to do is, well, number one, how about we label what we have? So v initial, that's 140 feet per second, or simply 140. Let's not include units because, well, we have a really big equation. It's going to have a lot of symbols. H, in this case, the initial height will be 2.5, and the angle theta equals 22 degrees. All right. When doing these calculations, well, notice we're giving the angle in degrees. Make sure that that your calculator is in degree mode. Recall, in some cases we use degree mode, in some cases we use radian mode, depending on the situation. Well, we'll write down the vector valued function r of t. And well, let's just plug in v initial, which is 140, cosine of the angle, which is cosine 22 degrees, times t in the direction of I, plus the initial height h, which is 2.5, plus v initial, which is again 140, in this case sine of the angle, times, or not sine of the angle, sine of 22. We have a numerical value, times t, minus, well, g again is 32, but 32 times a half, isn't that going to be 16? And we're using the 32 because, again, we're looking at the problem in feet, not in meters. So minus 16 t squared, and in this case in the direction of j. All right, so that's the vector valued function. And on the exam, it's going to be fine if you just give me this. No need to simplify this. Because, I mean, it's cosine of 22 degrees. It's a weird angle unless we have an angle for which we know exact values from the unit circle, like 30, 45, 60 degrees, you know. In that case, we're just reducing terms of roots of 3 over 2, 1 over root of 2, etc. You know those values. All right, so we got the vector valued function. Well, what is the maximum height? All right, let's go back to Calc 1. How do we find the maximum height?
It should be 0.
Well, something equals 0. Okay, something equals 0. When the velocity equals to 0, because the velocity is the what of the position. It's the derivative, so the maximum is found by setting the derivative equals to 0. Alright, but in this case we're not going to differentiate the whole thing because we're talking only about the height. The only thing that we will differentiate is the y component of the vector. Alright, so well, I don't know why it's trying to score. Yes. So note when the velocity is 0, but in this case the velocity in vertical direction. All right. So we are going to differentiate the y component of the vector valued function. Well, the derivative of 2.5. Let's write y prime of t. The derivative of 2.5 is 0. This is going to be simply 140 sine of 22 degrees times, well, the derivative of t, well, is 1 minus 32t. All right. So in this case, to find the max, well, just set it up to equal to 0 to find the critical value, which will potentially give you a maximum or a minimum. But in this case, we don't have to go through the entire first derivative test or second derivative test, do the table, because, I mean, it's projectile motion. We already know how this model behaves. We know for sure that this is going to be a maximum, right? So no need to go through all that madness. So set y prime equals to 0. So 140 sine 22 degrees, because otherwise no degree symbol means radians. And solving the equation, we get negative 32. T equals to negative 140 sine 22 degrees. And t will be negative 140 sine 22 degrees over negative 32, which is approximately 1.639 seconds. All right. But well, they're asking us for the maximum height. All right. This is not the maximum height. This is only the time where the ball reaches its maximum height. How do we find the maximum height then? Plug in, but where do we plug in?
Your position function.
In the position function for y, exactly. So maximum height y evaluated at 1.639, which will be y evaluated at 1.639. This will be, I'm afraid I'm not going to have enough space. So 2.5 plus 140 sine 22 degrees times t, which is 1.639, and then minus 16 times 1.639 quantity squared. And after simplifying all this, we should get approximately 45.476 feet. All right. Same idea. We get a critical number. In this case, well, it's understood that it's a maximum because we know how the model behaves. And well, to find the maximum, the actual maximum value, go back to the original function. However, here the new thing is that we have two components, an x component and a y component. So the y component is the one that gives the height. And well, let's use our graphing calculator to graph the path of the ball and determine whether it will clear a 10-foot high fence located 375 feet from the plate. Well, so here's the picture. After 375 feet, there is a fence, a 10-foot fence, a 10 feet fence. Well, we need to find the value of y based on our model here and determine whether it's going to make it through the fence. Okay, number one, what would be a good window here? So we're going to go to our parametric mode. Let's write down the window. The window I use for this is when t going from 0 to 5, x going from x going from 0 to 400, because I want to make sure that the 375 shows up in there. And for the y, well, since we know the value of the maximum height, well, which is 45, well, how about 0 to 50? All right, just so we can see a good picture here. So let me go to the graphing calculator. So these are the settings for the window, for the function. So let's go ahead and click graph. So, well, we sort of got the entire graph, right? Not necessarily well. So, of course, so let's see. So number one, we want to calc a value to determine whether it's going to make it through the fence that is 10 feet high. Well, so we need to find, number one, the x value for which the height in this case is 375. No, not the height, the position. Actually, the range is 375. In other words, so we want to know whether, so x, where is x of t equals to 375? That is, so that's 140 cosine 22 degrees times t equals 375. T will be 375 over 140 cosine 22, and t will be approximately I have 2.889 seconds, right? Now, what's the height at that value? That's the question. The height, we plug in this value of time on the y function, y of 2. I'm going to need space here. And so y of 2.889, that's going to be on the y component of the equation. In other words, 2.5 plus 140 sine 22 times the value of t, which is 2.89 minus 16, 2.889 squared. And after simplifying this madness here, we should get 20.47 feet. So the question is it going to make it through the fence or not? Yes, right, because the fence is only 10 feet. All right, and The height at which the ball is passing through the fence is, well, it's the point 2.889, comma 20.47. So yes, it's going to make it through the fence. All right.